So this is our flash, something like this. Inside our flash,
of the MCU.
Yeah, of the MCU. And inside this flash, you have usually two parts. When we are talking about bootloader, you have two parts. So one part is usually fixed, address reserved, and this is like first part, let's say, of the memory, and comes, usually it's a smaller part, something like this, and usually there comes the bootloader.
Is it like so a DOS on the motherboard of the?
Yeah,
yes, it is like DOS of motherboard. You can imagine it.
You can imagine it like this, but it is currently in the same hardware, the same processor, and BIOS has some extra functionality. So the first part of the flash memory is reserved for the bootloader, and then second part of the memory is reserved for the application. And that's what we have here. So we have a bootloader, and this is the application for it. Inside of this bootloader, you usually have some kind of functionality that you are able to fill up this flash memory, this rest flash memory. And now the other part of the bootloader is the communication interface. So he needs to get some kind of a commands from somewhere.
In this case it's a KNX bus.
In this case it's a KNX bus, but usually it can be UART, USB, CAN, or something else. And for the KNX bus, this means that we need to have here also the stack to handle all the communication from the KNX bus.
Small but simplified one.
It is the stack without the application.
But still a stack.
It's still a stack because it needs to have all the functionality.
This one is a stack, and here is also stack, so we have double stakes.
You have double stacks.
But the stack takes not much space, because the main one will be the application.
The stack itself will take exactly the same space, but in the bootloader you don't have any application. And here in the application you can write many code of the application.
Actually, so it will be this part, again duplicate this one, and the rest for the application.
The rest for the application. That's just a simple drawing. It depends on your micro. It can be bigger, lower, smaller. Usually this is inside Kyle. This bootloader takes about 25K or something. And then the rest you have with application. So this means I would suggest, if you want to use KNX bootloader, that you use at least MCU with 128K flash. And above. So from 128K flash and above. This is what I would suggest. You can try to squeeze it in less space, but
I understand.
So the two things we have is flash and communication interface, which is in this case KNX. Usually you have some kind of a protocols to communicate. So which kind of commands the PC and the micro are exchanging. So the bootloader and the PC, which kind of commands are they exchanging? And the most common way is, first the PC asks for some identifiers to check if this bootloader is really working on the device, if the bootloader is with the proper version, if it has the proper keys, I don't know, some identifiers he asks from the device itself. Then he can also ask some identifiers about the application, if the application is inside, so that he knows which application version it is, I don't know, application descriptions or something like this. Then the next part the bootloader does, he checks also the file that you gave him. So I can show you here how our application looks like for this downloading this stuff. System 15, utility, bootloader, release, and this one. So with this one here you open the file, and here you select KNX interface, because we have in same application two types of bootloaders. And here you are able to type, if you choose KNX, he will ask you then which communication interface you want. It will be this one, and it's IP routing. You have currently, routing. Yeah. This is.
So I think
This is power supply. Okay, this is power supply. This is also power supply.
Yeah. This is the main line.
USB.
Yeah, it's here.
It's here, and then this is a linear coupler. Oh,
yeah.
Line coupler.
Yeah.
Okay. So mainly you have here USB for communicating with all of this, right?
Yeah, but the thing is, basically the loader is working via the USB and via this one.
Okay.
And then to the bus, KNX bus, and to the target. Is that correct?
So he's doing from the KNX bus to the line coupler, to second line, to the USB. And these two are just supplying the lines, subline and
so the information you are sending will be from this place and then will go back to computer via USB.
Yeah, so basically the computer is the master in this stuff. Computer decides whether he should download, whether he should erase or whatever. So in this case, this tool of mine, this what I have here, will decide what to do. When I click here, now the KNX, he's asking me which kind of connection I want. So I can write here some name, USB connection.
So this is done by Falcon.
Yeah, this is a Falcon. This we took from the Falcon. We are able to use it. We have some keys from our side. And this can be used by every customer also.
Okay, but the thing is, in the real application, in case that I have my own device, one device, and then I will solve some bugs inside, and then so what should I give to the customer? So should I give some execution file to the customer, and so then after he double click, and then he can use from the USB interface, and then to program it the device on the target.
Yeah. So you will give him this tool, so all of these files, and this is exactly this tool. With Falcon built inside, because the Falcon you see it's here.
Yeah.
And he's able then with this one and the hex file from the new firmware to make.
Yes.
This hex file he can load to your micro.
Okay.
And then it should work.
So normally you zip it, for example, or the IR and send it to the customer.
Yeah. Okay. Yeah, it's something like this.
Yeah.
And now in this one I need USB interface. That's the one we are using currently here. But this USB interface has some trouble. Maybe cannot be open because
the ID is different or not?
No, it's here open. That's why.
It's used by someone else.
Yeah, it's used by someone else. Usually this is the trouble. I'm not sure, do I need to close the address? No, it seems to be working. Okay. And here you type your address. I don't know, address of the device.
Address of the target
of this device.
You want to download. You want to have a new text file.
Yeah. Okay. Either you're able to press here a programming button and click here get devices. And then he will read out the address of the device.
Sure. Okay.
So, and then here you load the file, the text file you want, find it, and click download.
Sure.
I will show you this later, just that I continue with this here.
Perfect, thank you.
Yeah. So first our tool from here, we open some file, and file has also some identifiers like the bootloader. He got already the bootloader identifiers. Now he compares it to the file identifiers, so that he compares the version that he can show it to the user. The second thing is he compares the IDs, so that this application can really go to this device, because it can have that you have 2, 3 different devices, and then if you try to load some hex file which is not fitting this hardware, then you can make a mess. That's why you can
I did that stupidly. So he will give me a warning that ID is not identical.
He will give you an error and he will not allow you to download.
Okay.
So the IDs need to be matching.
Sure.
Just versions are different, and this will be shown to the user. So current version is this, and the new version is something what you want. And this description you are also able to write in. This I will show you later. And now how does it function? After you click I want to download, he compared all the IDs and asked you for the version, you click yes.
Yeah.
And then he sends the commands to the bootloader to erase the memory. And so he starts erasing here to, I don't know how much memory it has, and erases the memory. And then the tool starts sending in the data to write in. So the tool is writing it in here. It can be also encrypted. So that, let's say, nobody can copy this your hex code and stuff. Yeah, because you can make
from the KNX bus via the device. Is that what you mean? Or the
everybody can read the KNX bus, but the hex file can be encrypted. So the hex file you create, there is a special tool we have here which can encrypt the hex file.
Just let's say just to prevent someone who is also on the same time on the bus when you try to load it. Will read this hex file.
Yeah, if he wants to read it in this hex file and copy it to some other device, that it's not possible because it's encrypted. So the MCU knows how to decrypt it, and this hex file is encrypted.
But then this space, if there is an encryption function, this one will take larger. Because we have to
currently we use some simple encryption. So this is just a few commands. But I think if some user asks for some special encryption method or whatever, we can implement it.
I understand. But in general, it's not a big issue, right? Because
but
in the KNX you are in a closed environment. It has the independent wire, so.
But the thing is, we deliver this download tool. But this tool for the processing, because it's very, very complicated, we usually don't deliver the source codes for this one. And this one, if you need to have it delivered, then we deliver it like libraries. So encryption, we have a few types of encryption. They are all simple encryptions. So it's just to mask something or to perform some more operations, but it's nothing special. It can be broken if somebody really, really tries, or I don't know. But usually the people, first they will never try to steal you some hex code when they don't have the bootloader at all. And what should they do with the hex code? They will need to, I don't know, copy the complete your hardware and then copy the bootloader, which they don't have.
And then load it. Understand.
The effort they can do in one meeting.
So we never heard that anybody tried to do something like this with but sometimes in the future we will have some possibility that it can be encrypted. So usually it's encrypted by this hex processing tool that we have here. So after the linking, after you make your application, this tool is called, and this tool calculates which parts of the memory should be written, erased, which part should be checked, not checked, I don't know, and encrypts also the hex file, so that this downloading tool which you send to the customer doesn't have any information about the encryption.
No, thank you. But sorry for interrupt. Before the teacher was telling us how to make this demo for application, but that's without a bootloader, right?
But that's without
bootloader. So now we are talking about in case that we have bugs, so the customer can refresh on site. But my question is, like at the beginning, then we were doing the manufacturing, and then when we load some of our application into the MCU, CPU, then we have to put a bootloader as well, right?
Yeah. So at the production, you need to
understand. But what he told us before, the only application without bootloader. So now my question to you is, how can we make the bootloader with the application he told us for the demo together, and then we can load into the CPU at the beginning?
This hex file processing tool does this also. He creates a merged file, bootloader and application, which you can load during production.
During production.
So he creates two files. One is firmware update, which is encrypted. If you want it encrypted, it will be encrypted, And the other one is this merged file, which he combines bootloader and application.
So this merged file, we can use the pins on the PCB, and then when the manufacturer it can be loaded.
With debugger or this kind of stuff. Now I forget that where was I?
Sorry about this.
Not a problem, just that I remember where was I?
You were saying for the workflow.
Yeah, the download procedure.
Yeah.
So he was writing the memory. After he's done writing the memory, there is a CRC check, and then he compares the CRC check with the CRC check he gets from this tool. So he performs the CRC over the memory from this one which he gets from the tool. The thing is, this other application has also this BCU sys which can be changed from ETS. It has these parameters from ETS inside the application.
Just hide on, you can say that please.
Application. Each application, let's say here, if I open it, this device, STI4, has some kind of parameter.
Samo sekund. Pusti si vremena ponovno vidjeti, kad završiš, onda dajemo te KAIstack kako se testira.
So, each application has some kind of parameters. It has some group objects, address tables, I don't know, association tables and stuff like that. This stuff is also loaded inside the application here.
Yeah.
To the segments which are called BCU and BCU sys. BCU sys. Yeah. Of course, during downloading the test, these segments can change because if you change some parameter, then the memory can start to change.
This part should not be updated.
And no, this part can be updated because it can be that you change some behavior with the parameters, with some macros, defines or whatever. I don't know. You change something with data. Usually not, but I don't know. Could be or whatever. So this hex file processing tool makes sure that this part is not checked by CRC.
Yeah.
So because usually it would fail and then it would say, oh, application is not verified. Why? Because you changed the parameters.
Yeah.
Doesn't make sense. This is all done with some kind of combination through the make files and then through the compiler linker, and then after the linker, this hex file processing tool merges this information, everything together, and prepares the files that you need for production and for the firmware update. What is done next? So if the application check passes, then the tool here gives the command start the application, and then waits a few seconds until the application is started, and then it checks also if the application is started. So he asks again, is the bootloader there, is the application there, what's the state? And then if he sees that the application is running, then he says everything is successful. If it breaks somewhere in the middle, during writing, reading, I don't know, checking the application, he will bring you this error and he will say, yeah, the error happened and the device stayed in the bootloader. Then you are able to download the application again. So the device is not broken completely, it's not functioning with ETS because it's in bootloader mode. But you are still able to download the new firmware, or when you discover what it is and you fix this in your firmware, why it was not working or whatever, you are able to download it again.
I'm not allowed to remove the power supply?
You are allowed here.
You're still allowed.
Because he will stay in the bootloader mode. This he will write in his flash memory, but he should stay in the bootloader mode. And he will stay there and wait, and when you disconnect it, connect it, he will still stay in bootloader mode and wait for the commands from the tool.
It makes no sense to enter the application, right? Because probably the application has been rewriting in the middle of the way and suspended, and then probably most likely the application will not work very well.
Yeah, application flash is somewhere corrupt. And when he enters the application, he doesn't know what could happen. What I want to say is more how this jumping to the application is really working. I can also, it's very simple, I can also explain it maybe through the code. These are all our files, let's say, for encryption, for a bootloader. And we're doing everything with the state machine so that it's easier to read for us. I mean, I'm not sure if the customers are used to it. This is CRC check. Is application valid? And also the ID is check. So if you accidentally loaded something with the wrong keys, which should not happen because this tool should prevent it, that he still checks it if this is matching. If it's not matching, then something is wrong. Yeah, he will not start the application. Switch update, no, check application, check and start. So what happens here is that after given a command to start the application, he performs first a switch. With the switch, he's updating this. He needs to update always the physical address and maybe some other stuff, so that if you change in the application the physical address, that the bootloader still knows this new physical address, and also if you change it in the bootloader, that the application knows this new new physical address, so that this information is not lost between them. So they are exchanging some information. And during this switch, he is usually disabling interrupts and making a restart. Why this? Because with a restart, it's the easiest way to deinitialize all peripherals.
But it's like a loading of application for the APS. After loading,
finish loading, he is restart. With the bootloader, it's the same here. He performs the restart, and then with this restart, he deinitializes all the peripherals. The first thing he does then is during BSL init, which I don't know where it is here. Maybe somewhere in main. Here. During this one, he's calling handle main with event restart. And this is done immediately after the startup. And then with the restart, if you have this set, so if your state is application should be active, then the bootloader does is stays at this state and performs check and restart. With the check and restart, he checks again if the application is valid. So all the CRCs, everything is matching, all the IDs. He saves this exchange flag so that the bootloader knows also the physical address and some other flags. This bootloader state, and so application knows this stuff. This one I want to say. And then he performs jump to the application. Inside this jump to the application, this is usually somewhere in the target, because we use this in multiple microcontrollers, so this is a target specific. Targets, SD, common, yes, the target. He takes the jump address. I mean, he's using it like a function. So reset handler should be like a function. He has some application information pointer. So this is one of these IDs, blocks, ID blocks, where he knows where the reset vector is. So where the vector table from the application is and where the reset vector is. Usually in this painting, if I want to draw it, it would be this here is the vector table of the bootloader, and somewhere here usually is the vector table of the application. Application identifiers are usually here, somewhere here. I'm not sure exactly, maybe these two are exchanged, but bootloader identifier is also somewhere here in the memory at the first part or whatever. But usually they are all at the fixed addresses, so that the bootloader knows where the application should start, and that the application knows where some bootloader identifiers are.
What is the full name of a BSL?
Bootstrip loader.
Bootstrip.
Bootstrip loader, but this is bootloader, bootstrip loader. To me, it's the same. I don't see any difference. I don't know what's this strip inside, but
alright.
Maybe there is some difference, but I don't know. So he takes the application vector address, which is hidden somewhere here at the specific position which bootloader knows. He puts this one as a jump address, so he performs then this jump to the application. This is this kind of function, so just a cast, jump address with a cast to the application, and then he jumps to the application. There is also here some kind of disable all peripherals, but I'm not sure is it really needed. Yeah. And from then on, this jump up from to the application, he's already here in the application, and now he starts executing code from the application. Do you see here the problem? There is one thing missing still.
And now we do something like the code.
If you now write some UART interrupt handler or some other interrupt handler, so I don't know, ADC or anything what you want to do with interrupt. The vector table, still this upper one.
The vector
table. So interrupt vector table is still this upper one. Yeah.
But the thing is, when you have ADC interrupt, but I don't think it's how come you go relevant to anything in the bootloader, because that was in the application, right?
So the application should have its own vector table. Like I said, it is located here at this position. But when I'm starting here now the application, the vector table he uses is still this one. Yeah.
So allowed?
Huh?
It is allowed to do that?
If the interrupts are disabled, like here, then yes. You see here, I've disabled all interrupts before jumping to the application. It's like disable interrupt. The thing we have is that during the startup of the application or the bootloader, any one of them, usually it's set always where this, how is it called, vector table is inside. In this one, I'm not sure if it's here or you have here F1, or I should put in F1. F103 is the processor.
Yeah.
Then move it in a standard peripheral library somewhere else. System file. So if this one is not defined, then define the vector table offset as 0. Then you will get the vector table here, and that's what the bootloader uses. If you define this, then you can ship the vector table anywhere in the code. This is usually by our stack defined. So immediately when you define where the border between the application and bootloader is, the vector table is automatically defined where it should be from the application. So you don't have to define this by yourself. It's done automatically. And now this vector table offset is defined with some value. And now you have here if the vector table should be in RAM. This is the case for F0 series. And this is for Cortex-M3 series. So this is for this one, F1, F2. They have this in flash that they are able to locate this vector table. And then it's just flash base with vector table offset. With this setting, we are practically making this offset of the vector table, so that the vector table finishes here. So everything you loaded now with the new application, he will take all the new interrupt handlers which you made. So in this way, I've seen also the bootloaders that are working, that they are masking these interrupts, so that you are always using the bootloader interrupts. But then in the bootloader interrupts, that they have some kind of a switches. When should they jump to the code from the application, or when should they jump? But this is a bit messy and a bit more complicated, and adds also a latency. So your interrupt functions don't execute immediately. You need some more time until the proper functions execute. So this is a much better solution, and this is available on these STM32 series, because this Cortex-M is allowing this kind of stuff. For F0 you would have For F0 family, you would have
F0 is M1? It's not Cortex.
It's a Cortex, but it's a Cortex M0.
M0, so M0 so has not so powerful.
Yeah, not so powerful instruction set and not so powerful processor options inside. For M0 you have also RAM.
Yeah.
And then usually this table is copied during the startup directly here in RAM. Because F0 is not able to shift it here in flash. It's only just able to say it's in flash or it's in RAM. So for the application, then we put it here in RAM and we say it's in RAM now, and then it's working. But for F1, it looks okay. Now to show you these identifiers, which I'm talking all the way around. We have it in System 15, Utility, bootloader. So these are the identifiers for the bootloader and these are for the application. Now we'll check what we have inside. This is one exchange segment, but first maybe you want to start from the bootloader segment because then it becomes more clear. So this is the bootloader info. So bootloader identifiers, we call it also info because it's a list of identifiers, some kind of. Bootloader version, CSC type that it supports. Currently it's 32-bit, I don't know, CRC something, but you can check the CRC hardware module of the micro to see which exactly it is. Maximal telegram length which it supports, it's usually, for the KNX, it's usually defined over this APDU length. So this is the maximal telegram on the KNX bus that device supports. Hardware software key, this is this ID which the tool here compares between the application file and the bootloader inside the micro. Because I don't know here what's this device, but if it has inside some bootloader where I define hardware ID is this and this, and now I make application for hardware ID exactly the same, then he will compare this hardware ID from here, hardware software key we call it, with the one from the application, and they two need to be matching. If they are not matching, he will bring you an error that you are not able to download this application to this hardware. Encryption type, if you want some encryption, these are some reserved for some kind of a future use, and also currently here for the alignment. This is where the application should start. So application will start application info address. So this is the address of this section here. I'm not sure which one comes first here. I will need to check it in linker script file or in met file. Also in met file. Because I'm talking these two, but I'm not sure really which one goes first. Bootloader application template. There is always something. File. File. Application info. Application info is immediately here. So it first goes application info. So this is this here part, and then goes in the vector table of the application. So the vector table is the second one. Okay. This upper one is some informations which are given to the hex file processing tool, so they don't finish up in.
So this met file will be created by the user compile. Using the one that compile. The bootloader together with the hex, the application. How does our microcontroller how do we generate this met file?
The file is created by the linker directly.
The linker.
During the build process. When it finishes up, you see then he doesn't have currently any finished process, but okay. When he finishes up, you see there text size, I don't know, data size, But in this moment, the map file is also created. Okay. So during linking.
Yeah. So from this map file, you can find the location of memories and
where everything is. Yeah. And you see exactly from which file is it coming and which section it refers to. I don't know which variables are inside or which functions are there.
Yeah, and then I don't understand is for the object file that you have, and after linking, then you get a hex file, right?
You get a hex file, or you get hex. It's not a hex file; it's executable file with debug information. It is like this here. I accept these two.
Okay. So then my question is, what's the relation between the hex file and the object file? Because I thought you first generate object file, and after you compile the linking or something, in the end you get a hex file. That's your expectation.
Okay, you want to know the difference between compiling and linking?
Yeah.
Yeah, this is okay. During compiling, let's say we take this C file.
Yeah.
He generates from this one an object file.
Yes.
But he doesn't know anything about all these other files. He knows only what is written in header. So let's say, in this case, he says, he's not referring here to anything else. Let's take a different file because this one I don't. Somewhere I have something that he's calling from outside. To be explained like easier. Some function where I can explain it easier. So let's say I take this file.
Yeah.
So now compiler comes, takes this file, and he's translating this to assembly.
Yeah.
Now he doesn't know for this one. This one is not inside this file. But somewhere in the headers, it's written that there is a function which is called like this. It returns some 32-bit integer, takes some 32-bit integer, and takes some length. So he doesn't know where this function is or assembly of this function. He doesn't know it. And then he just creates here a reference. So inside the object file, these upper ones he creates as assembly commands. And then here he creates a reference to the function which is called calculate.crc, which should look like this. So it should look that it takes 2 arguments and returns 1 argument with this much bits or whatever. This he does for each and every function. All this stuff finish up in the object file. So these are this.
So you can consider object file as some numerical input and multiple output.
You can consider it like a partial hex code, partial hex file. With just some smaller informations, and above this each hex file he has some kind of, this function is called like this. It takes these parameters. This function is calling at this place this function with these parameters, stuff like this.
And also return to maybe give. Does it return to someone in case another object file will need this information?
Yeah, he has each object file at the beginning has a list of files which it contains. So there you see this file has, I don't know, BSL handle main, has also is application valid. So all of these which are contained inside are in the beginning of the object file.
But then for the object file means that with the object file you don't need a header anymore, right? Because you already contain information of header inside.
Yes, you don't need any header anymore. So the object file has all these informations inside. Now, when I say the library is like you take all the object files and put it to a zip. So multiple object files inside one file, it's a library.
But it's still not linked to each other.
Yeah, they are still not linked to each other. It's just an object files
Yeah.
which are
Okay.
maybe inside this library they are, but
But for the object file, can you make back to the C file? No, not possible, right?
you can make it back to the assembler.
Oh, but the not the.
But to the C file, it's harder. Just if the object file is compiled with a debug option, then he puts also the comments to this assembler. He puts the comments like I write some assembly commands and then I put the comment. This is my C command.
Okay.
From these comments, maybe you can reconstruct the
C file.
But from the hex file which you deliver, there is no possible way that you are able to get the C code.
No. Yeah, but
you can just get the assembly without any kind of comment.
Okay, so even not possible to make back to the assembly.
To assembly, yes.
Yes, but without a notation.
But without any kind of annotation. So you don't know what's a function, what's a I don't know, what's a variable, what's anything, you don't know it.
Yeah.
He's just working with some registers there inside, and you just see these assembly commands and with no comments.
Sure.
Yeah. Okay. You don't know where the function starts, where the function ends, how is it called, you don't know anything. What it does.
Sure. In the library with a multiple object file, then what to do next? Maybe with the library. So with the library is including a multiple object file. Yes. And then with this one, what do you make it work to have a hex? So you have to link it.
You have to link it, yeah.
Okay.
So the linking means that the linker comes and takes object files.
Yeah.
And these libraries, which are a list of object files, takes this linker script, which we have at multiple places. We have these kinds of linker scripts. Let's say system 15. These linker scripts are just the definitions how the linker should work, where should he put which parts. Let's say this is one of it. I can open this one for the bootloader using Photoshop because it's not a Photoshop file.
But when you generate an object file, then can you get this linking file?
No, this is a special file which you write by yourself for the linker.
Okay.
I wanted to open it with a notepad or something.
Yeah. Editor or not?
Yeah. Just to show how it looks like. First, why is it used? To explain. Your linker. Your linker doesn't know which processor you are using.
No.
Your linker doesn't know where the processor's flash memory is, where the RAM is, where everything is. That's why these linker scripts or linker, I don't know, they call it also some linker commands and stuff like this are used to define your processor so that the linker gets the information where he needs to put it.
So linker is really target specific. So
no. Linker is not target specific. Linker can link everything. Compiler is more target specific because he needs to know assembly commands from the CPU.
Okay.
Linker is more specific, more general. So he takes the objects, he takes these rules, and then he combines the objects together and place it according to this memory that we defined in these rules. So linker is a very stupid program. It's not so how can I say high intelligence like compiler. Compiler has some optimizations and whatever.
Compiler do the job on when we change from the C code to object file, right?
Yeah. So we change. Compiler does this. He takes the C code, converts it to assembly, and then he gives it internally to the assembler, and then the assembler creates it to the object code.
Yeah.
And then you get this object file.
And then it's based on the assembly, right?
Yeah.
And then that means that the compiler has done this job.
Yeah.
But then now my advanced is with the object files, and then how to get the text file. So this one is not the job of the compiler anymore.
This is not the job of the compiler, it's the job of linker.
Yes. Okay.
So the linker takes the object files. As I told you at the beginning of the object files, it's usually set what the object file contains.
Yeah.
These functions, these variables, or whatever.
Yeah.
And the object file exactly says at which relative address to this object file are these positions. So where is this function, where is that function.
Yeah.
And now the linker takes all of these object files, takes all the lists, and then what it does is there is a command which is usually internally in the linker that the start is reset handler. You can also define that the start is something else.
Sure.
And then from this reset handler he checks the code. So the reset handler is calling this. This function is then calling this function, and this function, and this function, and then these functions are calling something else. And then he is building a tree. So which functions are calling what?
Sure. So who generates the linker file? Is it from compiler, from the KAI, or how do you get this linker file? How do you?
It's already in the environment. It's already in the compiler set. Because if you open here the compiler, let's say I have here compiler, archive, rcc, bin. This is archiver. This one makes libraries. This is assembly. So he makes from the assembler code object codes.
This one is making a library. The first one.
The first one is making library
from object code.
From few objects. So you give it just a list of objects and he's making your library. This one is making from the C code assembly.
From the C code to what's the difference between from the C code to object? So that
So this is how it's done internally. This one creates from the C code assembly. He's putting it all usually to some list files, which can be internally. Sometimes you see it, sometimes you don't. Depends on the compiler options you put inside. And then internally it calls this ISM. So
then you get
an object file. And this here is linker. So all of these are like a compiler set which you get with KAI directly. You don't have to write it. You don't have to do it. This one here. How can I explain? First I have to explain linking that I'm available to explain this one. So what does the linker do? He takes these object files, he takes the list inside, so at the beginning of the object files, generates the tree, and then he's linking together. So what he's doing is, according to this tree, wherever this C file says, I need this function to be called, so in this case, calculate CRC, he says, I don't know, CRC calculate block CRC. Here the C, so the compiler here left the empty space, and he said I need this function here. So the linker knows, during this tree I have to go to this object, and then in this object it said, at this address is my function which I need. And then he takes this address and puts it here, this position, so that he is able to call here this other function. I'm not sure if you are getting what I want to say. So the linker takes these object files, makes the tree, and links them together. So this is linking. So he's connecting between calls to the functions and between the actual functions. And then he's placing this all inside your memory, which is defined in this file which I opened here. So here I have defined flash sections, and this is what it goes to RAM. This is just a name, this is just an alignment, let's say to 0.
So when is this file generated?
This file we have made by ourselves, so we typed it in.
And then you need, and then when does it need it? When you generate when you link it, then you need it.
When I'm linking I need it. With these constants which we include here, you are also able to include in these scripts some header files. And from these headers he's able to say where does the flash start, where does the flash end, and stuff like this. It's like in a C file. If you include something, then you have these macros.
But this is only you made this file SCP is because of bootloader. If without bootloader you don't need to do that.
Without the bootloader you have to do it because he doesn't know where the processor has its flash memory or anything.
But I thought you already defined in a KAI, right?
car generates it for you. If you make everything inside the environment car, then the car generates this file for you.
Okay, this is my question because I thought.
Yeah, it's automatically in the background from the car done.
Yeah. Okay. But if you don't use a car as a development environment, then you have to create by yourself.
Yeah. Or if you use some kind of special things like bootloader. Then you have to create it by yourself because car doesn't know this stuff.
I see. Now I get a point because I was thinking in the car you can set up those things. Why you told me you still have to put it by yourself? Then I don't. That's why at the beginning I thought this one is target specific because it's for the car you.
Yeah.
Now I get a point.
Yeah. So this linker takes this script and takes all your object files and links them together, and then places it inside the memory. What you get as an output from the linker, let's say in your bootloader output, you get all of these, so these parts of file from the linker currently.
I mean after linking.
Yeah, after linking.
So we got this file.
So this one here is a hex file in combination with debug, with debug information. So when you are debugging, that he knows at which line you stop, which line of this, which C file is connected to which assembly command. So this and this, they are the same files, just different extensions because different environments use different extensions. Then it's easier for us to create both. They pretty much contain the same information, like you see.
So in what situation you need those two files?
When you are debugging. So let's say in Kai, I'll stop here. If I open here, output, demo dimmer, okay, here it doesn't have an extension that you are able to see directly. That's some built-in extension. But this is the point. When I click here, debug, he takes this L file or IXF file.
Okay.
And then he knows. You see here, he knows the address. And he knows that this address is linked to this C file exactly at this line.
I see. But
so this is a hex file with additional debug information.
I see, but then you don't know which file he now is using, right? Either it's the first one or the second one. I don't know which one is.
Kyle environment uses IXF file.
So Kyle uses
IXF file.
Okay. And
but if you want to debug it with mbits, let's say, then it's used L file.
Hex file with debug.
Hex file with debug information.
And with the C
debug information is
with the C code.
So debug information is just connection of the hex file to the C code. That you're able to go line for line or whatever. Do you see which variables are where in grammar and stuff like this? The other stuff he creates, I don't know what this HTML document is. I really don't know. This is something that Kyle generates, but it's, for me, it doesn't make any kind of sense. It means like it's like some kind of a cross-reference.
So
these are like he created like a help file directly called. As I see, he created a list of functions. How much stack each function uses and which function it calls. So this is like a list of chains. Like I say, when he's building the tree, then he uses this, which functions calls what. So this is like this list of tree which linker is creating.
Although it doesn't look like a tree, but it's
but it's
a flat.
He creates this hex file, which is this one without debug information. This you've seen already how it looks like. Probably. Do you understand it? I hope.
Sure.
I hope that I'm not too boring because he's not talking anything.
Can you go back to the compile folder?
Compile folder. Just a second. No. Where does he have it? In somewhere in manual. Say KAIstack manual. Okay. KAIstack. Compile. File.
Just quickly again, which function is for which?
So let's start here. This one takes the C file and creates it to assembler. Then this one takes the assembler, so the list file of the assembler, and creates it to object file. This one can create library from the object files. So multiple object files combined together create the library. This one takes also the object files, but it can create hex file and this IXF file, ELF file. Yeah. Okay.
And from ELF, the last one.
Show you when I come. I can tell it directly. You have this ELF file and IXF file. These two. They contain information with the debug. And this from ELF file is able to extract you the information outside.
What do you mean? But to make the from ELF into the hex, remove the debug information.
You are able to create hex from the ELF. This is one of the functions.
Yeah.
Or you are able to get information. How much flash is used, how much RAM is used, how much, I don't know, constant.
But why only from ELF, not from IXF?
Because IXF is one special format from KAI, and it's used only by KAI. I don't know why. And this from ELF is usually used in also other compilers. So I expect that the KAI has just took it from somewhere, modified it a bit, and I'm not sure.
Sure, thank you.
But it's called from ELF. It can work also with IXF files and ELF files, I think. And this is, if you've seen it after the build process, which I don't have currently here, no build process to show you. I can use it in, I can use it here.
From the command.
This one here already put some pause.
It's close.
Maybe use it also here. This is also the build command. Everything you see usually in this black window, it's now here in this window, but it's the same code. So this is now calling compiler and assembler behind. So creating these object files. Also, I think there are some lists, but I'm not sure are they shown currently here. Maybe this here. This. Currently. Oh, in this one it's not shown. Now we come to linking. And after the linking, see this, it's linking. And this here, what you get program side, this is from calling from ELF. So this information I get from this from ELF file. And then he says everything is linked. Then he's calling again from ELF, create the hex, and then create their hex. And this merge stuff, this is something that comes afterwards, but I can explain it also after. If I get back to the topic bootloader.
Sorry for deviation. We are not, to be honest, we are not the software coder, and then the one who's supposed to be here, but unfortunately he cannot be here. That's why we are here. So, we don't do a coding every day. So we do some, but not much details. So just sometimes.
But you can take this. You recorded it, and you.
That's the point. That's the point. Maybe this part, what the 30 minutes just spent, maybe it's not relevant to him, but.
But just that you're able to understand. Maybe he will find also some useful information.
Could be, also.
Maybe he will also correct me because I said something wrong. It doesn't matter. Okay.
You don't give me your card, so I don't know how to come reach you. No, just kidding. But we do it.
I will remind me later. I will come and give you. What I want to say now, where I stopped. This informations. There were the structured bootloader. It's better maybe to see. This is also already field code. If I open here the types, then you see directly what are the device info. Here, bootloader version, CRC type, Telegram link, hardware software key, And then this is here important. Application info address, this means where this other structure is positioned. So where the application info is inside the memory. So it means here I have some information which targets to this application info which is here. Then this is EPROM is used, so in your case nothing. Where the exchange section is located. So this means where this physical address, when they are exchanging between themselves, where this will be located, and maybe some other information like bootloader state, where this would be. And this is where the device infos are located, and these device infos are very important because they are types like serial number, hardware type. It is important information which should not be lost. And these two are also synchronized between the bootloader and the application, but it's only during the production. Once it's written, it should not ever be erased or rewritten or something like that.
Because yesterday you changed the manufacturer ID using the monitor.
Manufacturer ID is something else.
Oh, it's not inside this one. I thought I thought it was different.
But it should be done only in the production. So not outside this component. So when it exits the door, it should never be changed, manufacturer or something like this. So that's the same in your company. In your company, you are able to change it, but when you send it out to somebody, you don't want that he changes the manufacturer.
No, but he's able to change if he wants, right?
He should not be able to change the manufacturer.
ID?
Yeah, so...
how come that UTP they can change?
They have to buy the license for the...
the app.
With this one they are able to. But this is again the production. This is not, let's say, the installateur or the end customer which is using this. She will not be able to change it. So once the device is working and it's set up, it should not be changed. That's what I mean. So these are the things which should not.
But that one I'm talking about manufacturer is relevant to this address or not?
This is one special segment where this information is copied. Usually this manufacturer ID, serial number and stuff like this are somewhere in BCU, in BCU sys segments. But they are copied to these kind of segments during this synchronization, how can I say it? And it's only once done, so when you when you program it once, it is already inside and it should never be touched again in normal work. So in normal work you should be able to update your application with this tool, but this part should not be touched, not be changed. This part should stay the same and never be erased. So this needs to be in some kind of a special flash memory, a special flash page, which is never touched after the first production stuff. So these are a few important addresses. So from when knowing this structure, BSL info, which is always at the strict position, so that the application can access it and the bootloader can access it. Both know where it is. It's written with some special address, exactly this address. So with this structure, I'm able to move all the other structures because the addresses are contained here. So if I say that in the next application I want this exchange info to be in some other part of the memory, then I'm able just to place it in some other part and he will pick here the address of this other part. In this way the application and the bootloader can know where everything is positioned. So this is, I think, the first one which is important. The exchange info we have inside. So these are the information that they exchange together. We have some exchange state. We have some flags for the synchronization. So who should take which information from where. We have physical address, and we have also some field application error code if the application wants to report something to the bootloader. But this one is not commonly used by us. It can be implemented by the user if he wants. And these are for some special devices which support domain address. Then you have also the domain address inside. Domain address is, I think, some kind of an extension to physical address. So you have multiple domains, and then inside you have multiple physical addresses.
Yeah.
Something like this. Then the next thing, device info, what I already said, yeah, it has manufacturer ID, it has serial number, it has hardware type, and if the user wants some additional,
Yeah.
you can define some additional fields which you want to be synchronized or something like that. Now we come to the application. Application has two parts. Two important structures that I want to say. So the application has application info, which is loaded with the application inside the microcontroller, which is this here part of the memory, and it has some checksum over this structure. So from here to here, the checksum over this, so CRC checksum, is saved in this field. Reset vector address, so where should my bootloader jump when he wants to start the application. Has the hardware software key, so to check if the application is matching the bootloader. Has the application version number, does some dummy for alignment, and now the checksum blocks. Number of checksum blocks and checksum blocks itself. What is this? It can be here that my application, use some different color. This. This here. This. It can be that my application from here has this block of the memory occupied, and then this block of the memory occupied, and then next one, and that it has some kind of gaps in between.
Yeah.
Depends on how linker placed it, how you defined it that the linker should place it. Or that's why we need this kind of checksum blocks. This is nothing else than just saying start address, stop address, and the checksum of the block. So it just says this block here has start address, end address, and the checksum over this block should be something, I don't know. And then inside these gaps, or let's say it in this way, this is also good. So we have two blocks of the application, and we have BCU and BCUSys, let's say, which should not be checked. Yeah. And so only these two blocks finish up in this checksum blocks structures. Yeah. But all three are in the hex file placed. But inside this checksum block structure, there are only two. Let's say in this case. Yeah. What we next have is, so number of checksum blocks. In this case, it would be two checksum blocks, and then these two would be filled. And this here is maximum number of checksum blocks, so maximum number which you can have in this inside this complete structure. This means how much blocks can you have here inside this. If something is not matching the download, you fail, and then you need to search what's really missing, what's really not good. Usually this one is more than enough to hold all of these checksum blocks. What I have next one is this here, PC tool info. And this PC tool info is used for this hex file processing tool. So this is one part that comes, if you see it in the net file, it comes at the beginning of the hex usually. You can define it also at some other position. This is this BL info section PC tool info at the address 0. For some other microcontroller that has flash at this address, you are able to define it somewhere else, but then you have to, for the tool, also to define it somewhere else. And this is sent like a parameter to the tool, or it is in one file on the tool. Not sure. If you need it, then you ask it and I find it. This one contains the information . So this this is like a structure version. So if I change something to this structure, I can change also the version of this structure to indicate to the tool that we have some newer version. The tool needs to also know what's the flash erased value, so that it can exclude some blocks which are in the hex file but are empty. This is one thing. Or it can align the memory to the multiple of 4, because if we are using CRC 32-bit, this means that 4 bytes are always sent to the CRC calculation. So if our block finishes up with some uneven address, then we have to extend it that it is even, that we are able to send the last 4-byte block to the CRC. Data modulo is what's the smallest amount of bytes which you are able to send through the KNX telegram to write it somewhere. In this F1 is, I think, 2 bytes. In L1 series of STM is 4 bytes. In MSP, it's, I again think, 2 bytes or something like this. But depends on the microcontroller. Yeah, and this you are able to see when you're looking at the flash writing functions from the microcontroller. There it says usually write word, write half word, or these are the functions of the micro. Okay. Again, hardware software key, which needs to be matching with how do you call it? With the bootloader. Again, where the application info address is. And why is this important? Because our hex file processing tool will calculate the CRC over our file, over these blocks, and then he will put the CRC inside this CRC blocks. PSL info address. This is needed because of when you are trying to merge some hex file with the bootloader. So when the tool is trying to merge hex file with the bootloader, that you are able to send it to the production where they program it, then he needs to read out also the hardware software key from the bootloader file, and maybe some other informations to compare it, to say, aha, these two are matching together or not matching together, and how to place it in the memory. Application version, which is shown to the user. CRC type again, so that he knows which kind of CRC calculation over the blocks the tool needs to perform, because this structure finishes up to this tool. So this tool reads out this structure. Encryption type, then application description length, so this is the length of this kind of string, maximal length of this string, and this is application description, which is written here, application description example. If you want some parts of the hex file that should not be downloaded, then you are also able to define this excluded download memory areas, which are the same like CRC memory areas, so they contain just start address, stop address, and then he deletes these parts from the hex file. Encryption key length, if you use some kind of encryption, and then comes these memory areas, really download tools, excluded CRC, so download memory areas, excluded CRC areas, and encryption key if you have it enabled.
So when do you need to exclude the download? Why do we need it? For debug or so?
No, it's not for debug. It's usually if user made some kind of application where he wants to handle some part of the flash memory by himself, but he doesn't want that during download of the application that this part of the flash memory is erased.
Okay.
Erased or rewritten. Then you define it here. Usually, I have somewhere described how the process goes. I think first he deletes these things which should not be downloaded, and then he performs the CRC calculation over the parts which are defined in that should be CRC checked. Usually, if there is no CRC excluded CRC memory areas, then he performs over everything that is left after excluding this download, not downloaded or the next thing is, and this is more like important structures that we are using. After the PC firmware update tool is finished with this encryption and CRC calculation and this hex file processing tool, sorry, this one, when he's finished and creates this firmware update file and creates this merged file, the merged file doesn't have any more of this information, so this one is deleted because it's not needed for the debugger to load it. But for the firmware update file, you still have this information, only the encryption key length, encryption key, and type of the encryption, these are hidden. So that there is no information that can connect anything with the encryption tool. That the user can extract any information regarding encryption. This one. But it's still used for the firmware download tool to check all these hardware software key, I don't know, some other things. Now, I think this is mostly from these things. Just one thing here in the synchronization. We have this flex. Let's say this here, up there are the commands, this you see. Switch to bootloader, switch to application, enable download, check application state request. These are some kind of control state commands. Or then you have some reading info commands that the tool can read out the info blocks from the device itself. We have some download commands, so we reset address, send continuous data, so this is like a write data and wait for the acknowledge. And this is like fill data. If all the data are, I don't know, BB or something like this, then you can send just 1 byte and fill this memory with this data. Some error commands, error numbers. So if something fails during download, the tool is able to say what failed. These are the states of the bootloader. Some events for the state table. Some actions for the state table, so for the state machine. And now exchange flags. These ones I want to explain. Application first start, application updated, and factory reset. Usually, when you just now loaded the bootloader and he doesn't have any application, then you load the application. On top of it, this is called application first start. And then the application starts for the first time in the entire life of the microcontroller. And during this time, the application maybe needs to write some things in EPROM or I don't know, in Flash or whatever. And then after he has written all this stuff, then he resets this flag to 0, and this flag is never ever set again inside the same laptop. Application updated. This means after you download your update file with this tool, he will set this flag. So if the new application needs to synchronize some extra data or I don't know what, that he knows that he needs to synchronize again. And the factory reset, if you perform factory reset through the FS or I don't know, with some special button that you have on your device or whatever, then this one is set. And then the bootloader and the application know that this one is set, and then the bootloader does some stuff with factory reset if you need to reset something. And then the application does some stuff. If the application needs to reset something, and then it is reset again from the application, I think. So these are 3, let's say, exchange control flags. That you know which data needs to be reset, the exchange between the bootloader and application and stuff like that. The handling for these are just copying memory here and there, and I think it's somewhere defined in machine maybe, but I'm not sure. Maybe that I can find it later. Here. And she's checking if the application first start. He's checking somewhere else. These other flags. I would need to search for these flags to see where they are used. But mostly, this is mostly the bootloader functionality. Currently, this device doesn't have a bootloader, so if I try to load some example, it will report some failure. Check. Yeah. Okay. So bootloader example, we need bootloader application to load it. Output. You see here there are some more files, and these are the two files which I want.
Yeah.
This is
Why?
firmware update. This is exactly this one, just encrypted.
Ah, encrypted.
Encrypted, and with this additional PC tool information that
It is the same size almost.
almost, yeah.
Yeah.
Exactly. This one also has this PC tool information. Excuse me. So this is one should just be encrypted. This one. Check. Yeah. So they are mostly the same size. You see the addresses are the same. Here is the application.
Yeah.
But it says here it starts. This is this PC tool info, which you don't have in your merge file. So when I go lower, here starts directly the bootloader. At the right side, this is directly the bootloader. This is the PC tool info from the application example. And then after some time, you see here the bootloader ends. And here starts the application. And they are both not encrypted because this one you need for the production to download it inside. And this one is before processing, so before encrypting it with the processing tool. If I compare merge and preview, these are completely different. Because this one is encrypted application and this one is merged file. So these are everything in yellow. Maybe just one line with addresses or something.
So this one is only the application. This
Yeah,
one is
this is just an application with additional this PCU preview download tool information, or which is just used by the tool and then it is removed in this one. So I need this one to download. So here, but the grammatic is completely different, and the accent and the way they say the signs, or how do you call it?
pronunciation.
Pronunciation is
Intonation.
completely different. Intonation, pronunciation, accent is completely different. So there is not much together. Like I said, maybe 1% of the words come from this German origin.
But you have to speak the line because the German you have to speak German if you want to use that word.
I mean, if you are an engineer, maybe you don't have to speak with the computer. Like, and if you get around,
daily life.
But yeah, then when you come to a market, when you have to buy something and you want to express yourself, then you have problems.
But how do you learn? You send you to school?
Yeah, some things I learned through school, some things from some books. Like that some books which through English they explain in German and stuff like this. So some things from the school, some things from this. But before I came here, I didn't know. Because in the schools I didn't learn German. And it's just maybe.
Yeah, it was okay.
Yeah, it seems. It's a different device, but. I stole it from colleague. Mine?
No, so you also sometimes easy enough.
No. This is a confidential information,
Okay.
but you saw it
I know,
accidentally.
I know it's not, they don't do anything but internet. And we are also their supplier.
Okay.
So it's okay.
I mean, I took it from him. I didn't check what it is really because I took it fast, and yeah, I'm guilty to provide some information, misinformation. It is not use it, I think. But no. This I will feel like it is. Just once more, maybe disconnect it. So it's clean. If some process is using it or something like this. I have also some older tool, maybe the older tool will be better. This is close to better. You have this individual address. something else. I'm not sure what is it. It here knows what hardware should I have. This way
you
is
have
not
to
good.
match. Yeah.
And just try to send out something with group monitor to see if source address 10.254. This address I got it. Situation device, because it's used currently. Yeah. Sometimes I think the KNX is, and then I realize I exited. USB, KNX.
So you done all the tennis things when you join.
Yeah, the company. I didn't hear from the KNX before I joined the company. So I really need to find something. Why it doesn't work? Because nothing works on the first time. 15% of people. Maybe I need to also restart the computer, but then I will not, then I don't know the password. Let me go to this tool. This one is using built-in. This is some older tool which is using built-in Falcon. Just for the demonstration.
Yeah.
But later on, see it's different for in Windows. This is FS connection manager. USB device. I don't see it.
You sure that the driver has been proper installed for the
usually I wouldn't have this LED one. This one LED here if it wasn't installed.
Okay.
But on this one I don't even see it in USB connections.
Yeah. Well, that's communication parameters.
Connection parameters. So there is something like this. Because with this bootloader, I think we support both tools, this old one and the new one.
Yeah.
They have some different messages. Shouldn't matter that much. No, this one is recognized. And I don't know what address was it, but yeah.
With the press one up.
Yes, this is just. Application inside after this. And this older one is a bit slower because it uses different kind of messages. But I think it's still pretty good. It uses a bit shorter messages and it uses some user messages which were supported before, but according to the newest KNX specification, they are not supported.
No.
Yeah. But I think the KNX should be compatible, so I don't know why they cut out this code.
Yeah. So the reason was this support length.
It can be, I don't know, it can be length, it can be something.
Because the only hardware is the same thing, right?
Huh?
Yeah. Hardware is the same. We use the same hardware. The only difference is just Falcon.
Yeah, the Falcon is different, and the messages behind the Falcon that we use are different. But I never had this kind of trouble with the newest version also. I mean,
this was old one, right?